Let's talk about EPI. I will not tell the whole story about EPI, except if we have the whole night ahead of us. So let's focus on the key points regarding EPI, and the introduction is quite short from this aspect. The goal of EPI, on the overall objective, is to develop in Europe the intellectual property for a family of microprocessors and accelerators, having in mind to have something ready for the exascale systems that will be installed, as Marc has mentioned, at some point of time in 2023. So we want explicitly to address at first the supercomputing segment, but not only, because we don't want to have a one-shot project and then nothing behind. What we want is to create a sustainable business in Europe in the segment of microprocessors. I mean mid-range to high-end microprocessors, as opposed to the entry-level microprocessors you can already find in Europe at NXP, Infineon, or ST. So, supercomputer industry, so high-end microprocessors will drive the technology, and they are indeed in that segment driving the technology. And the discussion we just had is very interesting regarding the evolution of the technology, comparing x86 and ARM instruction set. But we also need to make business and make volume out of the technology we are developing. And this will come from the very main segment and vertical in the European economy, which is the car manufacturing industry. With the evolution of the car industry toward autonomous vehicles, to some extent to autonomy, to real autonomy, there is a need in Europe to have a European supplier for the electronic components, and I would say for the embedded brains in the cars, that we call in our own terminology the eHPC segment. So this is the high-end segment of edge computing. So this is mentioned here as edge HPC. So we will try to work on our two hands, HPC to drive the technology and autonomous vehicles to drive the volume on the business. Another key word for us is sovereignty. Remember that EPI was born in 2015 by a declaration of Jean-Claude Juncker, who was the head of the Commission at that time. And he said, I want to have by 2020 an exascale system in Europe based on European technology. And obviously, there were some deviation regarding the year for having exascale computing in Europe, but the idea was pretty clear, having something European, because through HPC, we can drive the demand of the European countries for sovereignty. GDPR is something that is well in place now in Europe. It works well. The Commission and the countries want to protect the privacy, so the data of the European citizen. There is a question of protecting the European industry regarding backdoors, leakage, of data leakage and stuff like that. And obviously there is a question of the real military sovereignty that is extremely important in Europe, in France, in Germany, and in some other countries, including UK. So sovereignty as a global keyword is also extremely important, and this is why the very first driver was to develop European IP, based on European IP and to create IP in Europe. So the core drivers, as I did mention, are HPC, automotive industry, on the longer term server segment and maybe European cloud segments. We can start seeing in Europe some initiatives to create a European cloud operators. That is a new trend in Europe, and we hope to work with them to provide them with the technology they could use in their own data centers. At the horizontal level, artificial intelligence and associated big data, because this is in the same trend, is something we plan to address through the developments that we have started. And they are also on the longer term, because there are very specific considerations for industry and robotics, very specialized developments for safety and critical verticals. So we have in mind industry, robotics, and obviously the space and the defense segment. So we hope that with the developments within EPI, we can irrigate all those segments which are very important for the European future. So let's have a look very quickly on the partners that we have in the consortium from 10 different European countries. There is no UK partner in the project. I would say unfortunately, because there is a very solid ecosystem in the semiconductor industry in UK. Well, let's say that we have indirect partners with ARM, where many developments are still in UK. But mostly, I would say, the main partners are from the semiconductor industry, massively French, from the car manufacturing industry, massively from Germany, and from the HPC ecosystem, so you can retrieve the usual suspects of the European HPC landscape: France, Germany, Italy, Spain, Nordics. Well, you can find all of them. And they will drive the development on the specifications for the needs of the European exascale supercomputers. So the key elements we have for developing the technology within EPI are, on the first hand, in hardware with the silicon and the IP, on the software, on the security. On the other hand, we make a complete co-design concept with HPC, automotive, and edge HPC as a whole. We don't design at first for HPC, and later on we will look at what the automotive industry needs. No, we develop from the beginning for the need in HPC and in automotive simultaneously, because basically they have the same needs. When we dig into the technical details in terms of, let's say, performance per watt, in terms of data rate, memory bandwidth, and stuff like that, it is surprising to observe that the needs in exascale segments and the needs for autonomous vehicles are almost equivalent. So it's not that complicated to develop together in a co-design approach for HPC and for automotive. And on the other hand, we also develop hardware, software, and security all together. So it's a full co-design approach on any aspect for the ecosystem and for the technology. It makes our life a bit more complex because we need to sync up many different streams of developments vertically and horizontally within the project, but this is much more efficient and we make a much better usage of the European money out of that co-design approach. So EPI develops intellectual property. The funds from Europe are from the H 2020 Research and Innovation Funds, so it's devoted for research and innovation. So we cannot develop products with EPI. We just can develop, and it is already something significant, intellectual property. So we need to move to the next step. So we need to move from the intellectual property to real products that will be in machines, and that any supercomputer designer or car manufacturer can acquire and buy. So to this specific purpose, a new company has been created. This is a silicon pearl, SiPearl, that has been incorporated last June, right now in France, and I am one of the founders of the company. And the company will be European. It could be located in any European country, doesn't make any difference, just a question of shareholders, depending on the funds that we are currently raising. The goal of SiPearl is to use the intellectual property developed in EPI to add additional intellectual property, to develop product lines, to manufacture, Cyper is a fabless company. Cyper is not Intel yet. That will come one day, hopefully. But anyway, in the meantime, Cyper is a fabless company. And Cyper will sell the products, the microprocessors, to any company who want to develop servers, computers, or supercomputers with this product. So that could be European supercomputer vendors like Ethos, that could be HP Crane, that could be Dell, that could be Lenovo, that could be Huawei, that could be any company indeed. There is absolutely no restriction, and I'm sure that the Commission would be extremely happy that the money of the European taxpayer is used for manufacturing computers in the US or in China. There will be absolutely no problem with that, because today the situation is not really symmetric from this aspect. So Cyper will be the industrial hand of EPI, and this is a very good summary of the specific situation of EPI. And Cyper is raising funds those days to complete the European budget, and the goal is to raise about 100 million euro or more before the end of the year, and we have very, very good expectations on this aspect, and we should make some interesting announcements about the fundraising and the round table around Cyper in the next weeks. So let's have a look on the roadmap on the technology, mostly at the hardware level today, because I will need much more time to talk about the software aspects. So this roadmap is obviously not detailed. I cannot disclose any technological details at this stage, but let's consider that we will get the first, let's say, prototype. We are going to tape out end of next year. That will be based for the general purpose processor on an ARM core, on an ARM NOC. The core is a Zeus core from ARM. Don't ask any detail about the core. I'm not allowed to disclose any information about it. And we are going to manufacture this, the first generation at TSMC in Taiwan with the N6 manufacturing process. This is the process between 7 nano and 5 nanometers. And on the first generation, we'll see that on the next slides. We will also embed top of the Zeus core additional computing tiles to as POC of future technologies that we will have in the second generation for the Titan, for the Chronos family. That will be a shrink in size of the first generation. That will be 5 nanometer, or it could be eventually better, depends. And we will also have at this time the Titan accelerator that is based on the RISC-V instruction set accelerator that we are currently developing. So that will be our first step with our own IP in the supercomputing segment. And the accelerator we are developing will be 100% European at the IP level in terms of development, and will focus on FP64 vector operations plus deep learning and machine learning for training phase. So there will be, let's say, a convolution engine inside the accelerator. So for the community can start using the technology, we plan to have with the first prototype that we'll get out of the factory in 2021, 2 systems that you can use. At first, there will be a PCI Express board developed by E4. That will be, to make it simple, a complete turnkey environment with a processor, memory, disk in a PCI Express form factor that you can plug in any workstation in order you can start developing at the software level with reasonable acquisition cost, obviously, to make the technology easy to acquire and to use. And in parallel to this activity, Ethos is developing a board that will fit in their Bulix Sequana supercomputer product line, the same way it's been done with the Mont Blanc project, when a ThunderX2 board has been developed by Ethos as part of the Mont Blanc project, and that became a standard product in the Ethos HPC product line. And then, by 2022, with the Chronos generation, we'll get the first mass market product, I would say, dedicated to the HPC segment, and we will release the Edge HPC version for autonomous vehicles that will be used by BMW for entering their certification cycle that is about 2 years long. That's very, very long in the automotive industry. So you should get the first European processor in real cars in the street by 2024, 2025. Let's have a look on the technology itself. So I'm sorry, it's not detailed. Obviously, this is a concept drawing, but you will have the main points here. So I'm going to finish with the question of the I/O and all of that. But let's start with the NOC, which is the network on chip. That is the internal glue in the processor. Basically, this is a mesh coming from ARM, and later we will replace the ARM NOC by the European one that is developed as part of the Mont Blanc 2020 project. So on this network on chip, that will be the glue for the memory access, the global memory access, and the cache currency protocol. We will let's say plug the Zeus cores. Don't ask me for the quantity of cores per die, a significant number. This is all what I can say at this stage. We will also have the POC of the European accelerator, so a very small elementary tile that we will test at N6 manufacturing process. And if it works, and we expect it's going to work from D1, then we will make a new mask where we will get thousands of this elementary tile to get the real accelerator. We will also implement the POC of a very special device that is developed by Calray for the automotive industry. It's a kind of specialized DSP with artificial intelligence mechanisms for the automotive industry. We also plan to embed an FPGA by Manta, a French company. So if you have a specific applications with a very stable algorithm, let's say an FFT or something like that, that you want to implement in FPGA, you can do it and you will get full access to the memory, to the global memory, to the cache currency at full speed of the NOC on the extra low latency for the memory access. So that could be extremely convenient to combine in your own models between CPU and FPGA. We will have our own specific cryptographic engine, so 100% European. That is a very good way to protect your assets and your data from any potential attack coming from whoever. And we have some customers who are really interested to plug their own IP on our chip. So for the external connection, we will get from the beginning HBM 2E. HBM3 IP is not ready, so we cannot use it yet. We will get DDR5 memory as well. We'll get PCI Express Gen 5. We'll get a high serial link, so that will be at the beginning with CCIX only for the REA family. And then for Chronos, we are going to move as well from CCIX to CXL, so we'll get both CCIX and CXL for the Chronos family. It's just a question of developing the IP, and that takes time. On something that is also extremely important for us, It's been extremely well explained by Jason when he talked about the AMD chiplet approach. We have exactly the same approach. Our solution is a multiple chiplet approach on an interposer. So we can have, for instance, one chiplet full of those core, let's say one general purpose chiplet, combined through the die-to-die connection with one chiplet full of whatever accelerator. That will be obviously the Titan accelerator, but not only. We plan to have a hardware development kit, and that should be on this slide. That is easy to understand. Through that hardware development kit, we are going to work with many different companies developing specific accelerators, so they can plug their own accelerator, potentially their own chiplet or just the IP, on our specific chiplets through the die-to-die connection. So from this aspect, I think we can easily address the needs of exascale supercomputers, where we observe in the US and the other places that developers are now considering to go to workflows, to very complex workflows, combining classical HPC with big data, with artificial intelligence, with many different topics. So each step in the workflow will require different performance units or different accelerators. So as one doesn't fit all, if you can at least have the same general purpose processor, let's say the same data proxy, controlling the different flavors of accelerators in a single environment, that will make your life as a developer much easier. So this is really what we intend to do with the concept of the common platform. So the goal of the common platform, that is part of the design from the beginning, the multiple chiplet concept of an interposer, this is to become the standard, at least in Europe, but maybe beyond, for specialized data processing engines. One word about the RISC-V accelerator we are developing. This is something very important for us. So the code name is Titan, and there will be a vector processing unit. So for FP64, FP32, FP16 and BF16, that should be 1024-bit long, so quite significant. And there will be as well a stencil/tensor component in the vectors for addressing the needs in the training phase of deep learning. As the elementary tile is quite small, there is a specific NOC for the accelerator, and we are going to plug this NOC to make a connection with the road NOC at some specific interface inside the global environment provided by the standard ARM NOC in a first step. And then let me finish with one slide about ARM. I think this is quite complementary with what we've seen. ARM was a very easy way for us to get a quick win in the high-end supercomputing segment. If we wanted to develop from scratch our own IP for having a general purpose processor in the high-end segment, we would have needed, let's say, 10 years, maybe more. And we would have been in a 10 years long tunnel with absolutely no success. It's not manageable. So we decided in a first step to go with ARM, which is an existing IP, and this is their business to sell IP. So they are quite neutral. It's a UK company. It was born in UK. It's still now it's a Japanese company, but the HQ is in UK. So it's okay. There is no problem. And through time, through the long-term industrial vision we have in Europe, over 10 years, maybe even more, then we will develop, based on RISC-V, our own IP. It's a long way. It's a long story. It's a long journey. But this is really the intention. So starting with ARM, we don't start from scratch, There is obviously many different initiatives around the world, starting with Europe. So we have discussed the UK initiative, and I would say that complementary to that, there is the Mont Blanc EPI initiative around ARM. In the US, they also have a strong initiative around ARM architecture. So with Cray, with HP, so now the same company, that makes the life easier. There is Marvell as well. And Sandia is leading the initiative in the US. In Japan, they started long ago at RISC-V, and what they are doing is really amazing. What Fujitsu has developed is a great technology. The vision of RISC-V for their own post-K machine is really impressive. And Mark, I think it was in your presentation that the goal of the Japanese guys is to have a machine that will stand very long. And this is really a good summary of the vision of the Japanese people. So we work more and more closely with RISC-V on the development of the ARM ecosystem. But even if those days China is not, let's say, with a strong momentum, and Huawei, it's even worse. They are working on ARM. They have acquired a complete architecture license. They have created a local joint venture with ARM, and they are forked from the mainstream development at ARM. So they are developing their own ARM-based stuff. So at the worldwide level, there is a strong momentum around ARM architecture, and I believe that in the future we will have a world with x86 on the first hand, on ARM on the second hand at the instruction set level, but ultimately for the users that will make no difference. Because as long as there is a good compiler, good libraries, good development environment, and good performances, what's beneath the computer, you don't mind. If it works, it works. What's the instruction set? Do you care to have an ARM system in your phone? No. So it's not a big deal. As long as you have equivalent results, and it was interesting to know that there was a focus about results in the previous presentations. Not same performances, but numerical results are equivalent. This is the most important. Everything else, you can forget it. So, but for the people funding the projects, having a healthy competition and an open competition between different processor vendors is something extremely positive. So ultimately, for the taxpayers, it's even better. So that would be my conclusive words for today. And next time, I will dedicate my talk about the software environment in EPI. Thank you.